going to take a closer look at these non-right triangles and hopefully see if we can find some relationship and come up with some easier way to solve these non-right triangles. And the relationship that we're going to come up with is something called the Sine Law. So when we solve non-right triangles, we're going to split it into two right triangles using this height here, or the altitude sometimes we call it. And when we look at this triangle, what can I say about this side length, the angle alpha and angle beta, and the opposite side B and the opposite side A? Okay, well, let's see what generalization I can make. I can say that if angle alpha is smaller than angle beta, so let's draw this a little bit shorter, this side length A must be smaller than this bigger length B. So we're going to say that side A must be smaller than side B. Well, what if the reverse is true, like I've drawn it here? Beta is smaller than alpha. Well, we can see that this side length B is shorter than the side length A. So if angle is smaller, we can say that the side opposite is smaller. So this side B then is smaller than side A, and that's what's been drawn here. A is definitely longer. So is this relationship a direct ratio, meaning that if I double A, I double the opposite side A, and doubling angle, doubling the side? Well, that's not true. Okay, so I'm going to put a big no here. And I can kind of show this by splitting this angle kind of in half, and I can see that as I take half of that angle, this piece is not half of the whole length. So there's not this half-half or double-double relationship. Okay, so this is not a direct relationship. It kind of makes sense because this angle is a degree measurement. This side length is a length in like meters or centimeters, and they're really totally different measurements. And it's hard to connect the two properties together because this is a turn and this is a length. To do geometry, we really like to be able to just compare length and length. So we're going to see how we can maybe do that. So basically, there is not this direct relationship. So if I take 70 degrees and side A, I can't say 35 degrees is going to give me half of angle A, half of the side A. Okay, that doesn't work that way. Okay, so there's not this direct or proportional relationship. So how are we going to relate this? Well, we're going to try to relate the angle to a side length. And the side length that we're going to relate everything to is that H. So that is the common side length in both the right triangle, which I'll do in blue. Actually, I'm going to do this in a different color here. We'll do that one in red. And that side length H is also common to the left-hand right triangle, which I'll draw in green. So that height is what connects the two halves of those together. So height, that H, is what connects the right-hand triangle with the left-hand triangle. And so how can we start connecting the angles to the side lengths? Well, we're going to do it using the sine ratio, where we connect the H divided by A is equal to sine beta. So if I want to express the length of H with angle beta and side A, so the red triangle here, I'll show the ratio H over A equals sine beta. Well, that means that H is equal to length of A times sine of beta. And what I've done is, by using sine, I'm actually talking about a ratio or side length. And now we're talking about a side length in terms of A and the angle. So I'm going to write that down. The H is equal to A sine beta degrees. On the right-hand side, the left-hand side, I want to relate angle alpha and side B to side H. Well, I can do that using my sine ratio again. H over B is equal to sine alpha. And so the height, I can write it as B sine alpha. And so that's what I'm going to do here. I'm going to write this as B sine alpha. Okay. Now, how can I make these equal? Well, these are the same heights, so I can make them equal to each other. So I can say that b sine alpha, okay, because they share the same height. H is some length. It's not a ratio, it's a length. And I've got expressions for the same length, so I can make those expressions equal to each other. So A sine beta is equal to B sine alpha. And in fact, I want to just be able to put the A's with the A's and the A's with the alphas and B's with the betas. And if I just rearrange this, I'm going to have something like this. I could just cross multiply A over sine beta is equal to B over sine alpha. And so what I've come up with then is I've come up with a ratio that connects the sides. So I've got angle A, alpha, and the side opposite A. That ratio is constant for the whole triangle. So if I have a angle and side opposite pairing, if I compare the side B with angle B, or sine of the angle B, this ratio is consistent for well, I've only shown it for two sides of the triangle, but this is actually true for all three sides of the triangle. So I'm going to, in fact, add in that this holds true for sine of side C compared to sine of the angle gamma. So this is going to be the same, and gamma is, these are side and angle opposite pairing. So there is this law called the Sine Law, and it works. This ratio works when we have angle and side opposite pairs. Okay, so this is something called the Sine Law, and we can actually now, instead of splitting this up into two right triangles, I can just use the actual triangle, and if I connect the angle with the opposite side, I can make a ratio with these two parts, and I can make an equivalent ratio with these two parts, and I can solve for any unknown parts that I have.